Making progress. Alrighty, good morning, everyone. So today we're going to start chapter 17, which will be the second chapter for this upcoming exam. So see how all this goes. So basically what chapter 17 wants us to do is it wants us to start looking at the comparison between Coulomb's law, which is the force between two charged particles, and the gravitational force, or Newton's universal law of gravity, which is the gravitational force between two massive particles, right? So let's say if I had two objects here, where this has a mass 1 and charge q1, and this has m2 and q2, separated by a distance of r, then we know that what the gravitational force between the two, so let's call this F sub g, or I'm looking at the magnitude, is equal to gm1 m2 divided by the distance r squared, where the electrical force between the two is then equal to K times then the magnitude of Q1 times the magnitude of Q2 divided by the distance of R squared. Now, what it really wants us to do is basically compare these two things together. So we see they both have a fudge factor. So this one has the electric constant K, this one has Newton's gravitational constant. They both have a product of two objects, where this is the product of the masses and this is the product of the charges. And more importantly, they're both inversely proportional to the distance squared, right? So they both go as 1 over r squared, where again, there's a little bit different. This one is always attractive. This one can be attractive or repulsive. But what's important here is that they have exactly the same structure. Okay? So these have exactly the same structure. Now, why is that important? Well, that's important because we know the gravitational force is a very particular type of force in the fact that it's a conservative force, right? So we know that this guy is a conservative force. Now, the fact that this guy has exactly the same structure as this guy makes us say then that, well, since this guy and this guy have exactly the same structure and this guy is a conservative force, then this guy should be a conservative force as well, since it has exactly the same structure to it. So we can pretty much infer that our newfound friend, our Coulomb's law here, is also a conservative force. Now, I think you guys told me this during the first week of classes, but why do we care so much about conservative forces? So why are conservative forces important to us as opposed to non-conservative forces, which exist? But why do we make such a big deal? We spent an entire chapter, I mean, you said 175, you guys spent an entire chapter on the fact that you had conservative forces. Why are these things so important to us? What do they let us define? What do they give us? So important about conservative force.
I think it's like when we use like conservation of energy, like zero equals it.
Good. Stick with the conservation of energy part. Exactly. These things allow us to define an energy because they always act the same way, right? Unlike friction, where, for example, if I slid, oh, somebody was nice to put the eraser that I threw across the room on the table. So if I push this thing, I'm not going to throw it. If I push it across the table, for example, and I push it like this far versus if I push it like this, the amount of energy I lost in one scenario versus the other scenario is not the same, right? So if I had a non-conservative force, then the amount of energy that changes going from one position to another position will be drastically different depending on the length of the path that I move it under, which means that even though I can start and finish at the same spot, so if I go from here to here for a non-conservative force versus here to here to here, I lose more energy doing this than I do this, which means it depends on the path. For a conservative force, it means it doesn't matter, in this case, gravitationally, if I move it from this position to this position, or if I move it like this, as long as I start and finish at the same points, it doesn't matter how I move it from one point to another point, which means that conservative forces are what we call path independent, where non-conservative forces are path dependent, which means that conservative forces allow us to define a potential energy. So what this means then is that we can define a potential energy. Right. And then, as Maddox just said, the most important thing about that is that allows us then to use conservation of energy. So the point of all this is that, again, the gravitational force, which has a structure identical to that of the electric force, is a conservative force, which means the electric force would also be a conservative force. And since they're conservative forces, that allows us then to define a potential energy. And since we have potential energy, we can then use conservation of energy to do whatever it is that we want. Okay? So this is what we're looking at in this chapter. So basically what we want to do now is say, well, the electric force is now a conservative force, which allows us now to be able to define a potential energy. So the first thing we're going to look at is what is the work done, and then remember how the work relates to potential energy, and then be able to look at the potential energy from there. So I brought this thing in, this nice little toy here. This thing is what's known as a cathode ray tube. So this is actually what used to be inside of old TVs. So if you're an old person like me, you used to have tube TVs. This was the back of the TV, which was a tube. Inside of here, basically what you do is you plug it in, which then creates a potential difference. That potential difference then, oh, tell me. Hello. No problem with that. The light is on, right? Is something unplugged that I can't see? Okay. It says it's on. It's getting powered, but for some reason it's not doing anything. It worked just fine yesterday. Tracker position. It's still on. What is that? Okay then. Well, that ruins the entire fun. But anyways, basically what should be happening is that I should be having a beam of green light across here. Let me play with this for just a second. I wonder if I broke the fuse yesterday. No. Maybe a broken wire. I'll have to get a new wire. Oh, well, we'll play with this in a minute. But basically what would happen is like inside of here, what happens is I create a huge electric field inside of here because I have a positive side on one side, negative side on the other side, which creates an electric field. Inside of there, the electric field becomes so big that it actually starts ripping off charged particles from the gas that's inside of the tube. Once it does that, it then starts to accelerate those charged particles from one side of the tube to the other side, which then would actually give you this beautiful green beam that comes across here. Hopefully, if I can get it to work. Now, what I also know is that that beautiful green beam that we see is actually the interaction of the particles with the kind of paint that's on here. And I can actually show you that that's true because if I take this, which is what's known as a neodymium magnet, the thing I was going to show you is if I move it around, it can actually cause the beam to dance around and deflect, which means it's not light, it's actually charged particles which are moving. We'll talk more about that for the fourth exam. Okay? But basically what happens then is I can use this to then determine the amount of work it does to move a charged particle from one side to the other side by basically imagining that this thing is nothing more than a parallel plate capacitor. All right, so let's do that. I'll come back and play with this later and see if it can actually work by the end of the day. I don't know why it's not working. This room just hates me. Anyways, so let's go ahead and do that. So let's say this thing is a huge parallel plate capacitor. So I have a positive plate on one side, a negative plate on the other side. So let's say this is positively charged. Reminds me how my balloon didn't work either. So makes me think. Anyways. And let's say this side is negatively charged. And then we know that we get an electric field which points from the positive side to the negative side. So this is then my electric field. Now, we know also that inside of the plates, the electric field is simply a constant, as we talked about over the last couple of days, where that constant is simply equal to the charge density of the plate divided by epsilon naught, right? But in this case, the important part is that the electric field magnitude is simply equal to a constant. Don't worry too much about what that constant is at the moment. Now, again, inside of here, what's happening is I'm stripping off a charged particle, which in this case, I'm going to pretend is a positively charged particle. And I'm going to strip it off very close to the positive plate here. So I'm going to call this point A. Okay. Now, what we know is since this is a positive charged particle, this is an electric field. This guy then is going to feel a force in which direction? Go to the right. So we know in this case, since it's a positive charge, it has to feel a force in exactly the same direction as the electric field, which means the electric force is going to be pointing off in this direction. Which means this guy then is going to be accelerated and it's going to move across, increasing its velocity until eventually it hits the other plate on the other side, which I'm going to go ahead and call point B. So what I want to know then is how much work then by the electric field to get this guy to move from one side to the other side. Now, just to remind ourselves, work is equal to the force times the distance times then cosine of the angle between the two. Mm-hmm. In this case, this is going to be our distance, the distance from A to B. And then in this case, since the force is this direction, it's moving also in this direction, which means D as a vector points this way. This is my direction D. What's then the angle between F and D? 0, and cosine of 0 is equal to simply 1. So following this guy, this is going to be the electrical force times the net distance of D. Now, we also learned yesterday that force can also be written as charge times the electric field. So this is going to be then equal to the charge of the electric object of the charged particle times the electric field between the plates times the net distance of D. So this is going to be the work done by the electric field. Mm-hmm. Now, simultaneously, we know the work relates to potential energy by then equaling a negative the change in the potential energy. Okay. Now, we can learn a bunch of different things from this. So first of all, remember, so this says that the change of potential energy then is equal to negative the charge times the electric field times the distance. But remember, potential energy or any change is going to be the final potential energy minus the initial potential energy. So it's going to be the potential energy at B minus the potential energy at A must then be equal to negative QED. So let's take a look at this for a second. So what we know is that the initial potential energy is at A, the final potential energy is at B, which means it moves from A to B. But since the change going from A to B is equal to a negative value, what does that tell us about the potential energy at A versus the potential energy at B? A is greater, right? So this says that it actually moves from a region of high potential energy. So this is our high potential energy region. To a low potential energy. Now, does this make sense? Well, let's think about something like an eraser, right? So again, depending on where I define my 0 to be, but we can all establish that what? How does the potential energy here compare to the potential energy here? It's higher up here, right? So this thing, naturally, if I let it go, it's going to fall from a high potential down to a low potential. Right. This thing, my charged particle, is also going to do the same thing. It's simply going to fall downhill, going from a high potential energy to a low potential energy, exactly the same way that this eraser is going to move. Now, if I define my final potential energy here to be 0, what this also tells me then is that the potential energy is then going to be equal to simply what? The charge times the electric field times the distance. So this is my potential energy or the electric potential energy. Now, one thing to pay attention to here is that this is only true for a constant electric field. Okay. So this is only true, so it's going to asterisk here. So only true for a constant electric field. Now, the other thing to note is that if the electrical force is somehow not exactly parallel, but somehow perpendicular to the distance here, then in general, this is going to be written then as Q times the electric field times the distance times cosine of the angle between the two. It's actually more of a correct statement. Okay. Now, if the electric field is not constant, in that case, we'd have to actually do an integral, but we'll kind of skip that part. We'll go around that. So good. So this tells us multiple things. Again, first thing it tells us is that it moves from a high potential energy down to a low potential energy. The work is equal to QED, which is equal to negative the change of potential energy. And then from there, we're going to find the potential energy is simply QED times cosine between the two. Now, from here, it's actually more convenient for us to define a new quantity. So let's define this new quantity. This new quantity is what's known as the electrostatic potential. So what is the electrostatic potential? So the electrostatic potential, we're going to call this guy V, where V then is going to be equal to the potential energy per unit charge. This is what we call the electrostatic potential, or most of the time, we're simply going to call this guy the potential for short. So anytime you hear me say potential, what I really mean is electrostatic potential, okay, which is the electrostatic potential energy per unit charge. So this thing has units of joules. This thing has units of coulombs. So this has units of joules per coulomb, which gets a very special name, which is what's known as a capital V. Also, it's known as a volt. So a volt is a joule per coulomb, which is the electrostatic potential energy per unit charge. This is what we call volts. Now, as we talked about in lab, I'm going to re-talk about it again. It turns out that this thing has an inherent built-in ambiguity because potential energy has an inherent built-in ambiguity. So as I mentioned in lab, so again, if I held this thing here, how much potential energy this thing has depends on where I define my zero value to be, right? So where my reference point is. So if I'm talking about the top of this as kind of a small potential energy, I'm talking to the top of the table here has a little bit higher potential energy. From the floor has a bigger potential energy. The first floor is building even bigger potential energy, and et cetera. Right? This thing then has exactly the same built-in ambiguity to it. So it has the value of the potential at a given point doesn't really have much meaning until I know where the zero or the reference point happens to be. Which is why, just like potential energy, what we're really going to care about the most is actually the change in electrostatic potential. Let's talk about the change in electrostatic potential. So the change in electrostatic potential, call that guy delta V, is then going to be equal to the change in potential energy per unit charge, which is then equal to minus the work per unit charge. So this is what we call the change in the electrostatic potential, or this thing is also what's known as the voltage. So voltage then is actually the change in electrostatic potential between 2 points. So in this case, for example, if I was using the notation I have here, this then would be equal to the potential at B minus the potential at A, would then be equal to the change in potential energy at B minus the potential energy at A, all divided by the charge. So this is what we call the voltage. Okay? So the voltage then is the change in potential between 2 given points. Now, again, just like potential energy, again, if this thing only fell from this height to this height, I can arbitrarily call this guy 0. This guy would be non-zero, and then I just look at the change going from here to here. Doesn't mean this guy actually is 0. I'm just conveniently defining it to be 0 just to make my math easier, right? So again, this is the same thing. So this means that, again, as I talked about in lab, if I took my voltmeter, so here's my voltmeter, and I put one wire here, and then I put another wire here, and I found that this was, say, 5 volts. Again, all this means is that this is the difference in potential between A and B is 5 volts. Doesn't mean this is at 5 volts and this is at 0 volts. It just means the difference between the two is 5. Now, again, arbitrarily, we can always say this is 0 and this is 5, just for fun, right? Just to make our math a little bit easier. Now, again, here, it's easier to work with the potential because, as we talked about in lab, and we'll make it more straightforward a little bit later, is that it's a lot easier to measure as opposed to potential energy, because here all I need is a voltmeter, and that voltmeter then will tell me the difference in the potentials going from one point to another point. But based then off of this, I can then find the change of potential energy by simply taking that voltage and then multiplying by the charge. So the beautiful part about this is that now this saves me that my change of potential energy between 2 points is then simply equal to the charge that's being moved times then my change of potential. Now, what's beautiful about that is exactly what Maddox said. Now I can take this and simply put this into conservation of energy. Right? So conservation of energy then would say that what? My work done by my non-conservative force is then equal to my change in kinetic energy plus my change in potential energy, which is then going to be equal to my change in kinetic energy, plus then the charge times the change in electrostatic potential, or the voltage. So this is going to be now our new expression for conservation of energy, as long as we're dealing with electrostatics. So all this means is all I need to know is what's the change of potential going from one point to another point, the charge that's being moved, and that's all I need to know. So these are just going to be values. And again, this is something that's nice and easy to measure because most of the time all I need is a voltmeter to measure that. I don't need to know how it's changing from point A to point B, just that it changed going from point A to point B. That's okay. So let's use this. Let's do a couple examples while this thing is firing up. The other thing I'll mention is that what? Since potential then is directly related to the potential energy per unit charge, that means that this side is actually the high potential side, and this side is actually the low potential side. So what that means then is the positive plate is the high potential and the negative plate is the low potential. Okay, so that means if I gave you a problem where I say the left-hand plate is the high potential, that means it's telling you it's the positive plate, then the right-hand plate then would be the low potential, which means the negative, which tells me the direction of the electric field. What's up, Jackie? If I had a negative charge, what actually happens in that case is that the electron goes uphill. So it's a little bit opposite. So imagine that if this was a negative mass, what happened in this case is that it would not spontaneously go this way, but it would spontaneously go this way. So a negative charge actually climbs uphill, it doesn't fall downhill. Yeah. Well, it would still, because we consider it based off of the positive charge, not a negative charge. Yeah, so a negative charge would actually go from low potential to high potential. So, I mean, if you're thinking about the viewpoint of a negative charge, then yeah, you can call that the high potential side. But usually when we use this naming convention, we're talking specifically about Q is always going to be positive. Exactly. Which is why, yeah, negative charge is a little bit weird because it actually goes from low potential to high potential, does the opposite. Yeah, which is important for things like batteries. So, it's okay. So good. So let's do a couple of examples. So this is in the figure below, I have a parallel plate capacitor where I have two plates. One is at a voltage of V1, the other one is at a voltage of V2, where V1 is negative 70 volts and V2 is at negative 50 volts. They're separated by a distance of d, which is 2 millimeters. And then I have some charged particle. Here's my charged particle, which is going to be initially moving to the right at a speed of 90 kilometers per second initially, but it's going to be slowing down by the time it gets to the second plate. Okay, so it's moving towards the second plate, but it's slowing down. So from here, it then wants to know, is this particle that's moving, is it a proton or an electron, and why? And then once we know if it's a proton or an electron, what is the speed it has by the time it reaches the second plate? So this is what we want to know. So basically keep this thing here. Great. So here are my two parallel plates. So it says that this one is V1, where V1 is equal to negative 70 volts. And it says that this one is V2, where V2 is then equal to negative 50 volts. And then the distance D between the two plates is 2 millimeters. One thing I should point out is notice I have different V's. So when I write these, there's a reason why I write them differently. So if I write a V like this means velocity. Just so we know which V's I'm writing about. If I write a capital V with a solid bar across the top, that is volume. And if I write a capital V with 2 bars or a split bar, this is equal to voltage. Right, so this is a volt. But just so you know which V's I'm writing from time to time. So and when you're kind of writing quick, you can't tell if it's a small v or a big V or whatever. So that way you know I'll always do this. So you know which V I'm actually talking about. So good. So now we also know that this thing has the charged particle. Charged particle is here. Let me get rid of this. And then let me call this the initial velocity. So let me call that V0. So we know V0 is moving here. And we know that by the time it gets over here, has a final velocity moving in this direction V, where this velocity V is less than the initial velocity. So it's slowing down. Good. So first thing we need to know is which side, oops, I should probably get all my positive and negatives out of here, so we don't know which one's which. We now want to know which side is the high potential side, which one's the low potential side, meaning which side is the positive plate, which one's the negative plate, so we can establish the direction of the electric field. So we can then determine if this is a positive charge or a negative charge. So let's do that. All right. Now, first things first, this is negative 70 and this is negative 50. But if I wanted, I can establish one of them to be 0 and then the other one non-zero, right? So which is the easiest one to make 0 in this case? Probably this one, right? So I'm going to arbitrarily instead call this guy 0, which means I'm adding, what, 70 to this one. So I add 70 to this one then is going to become what? A positive 20 volts. So I have a 20 volt difference between the two. So if this is the high potential side, this one is the low potential side, which one is the positive plate and which one's the negative plate? Positive and negative. Good. Got. So this side is my positive plate. This side then is my blue, my negative plate. Great. So that, which means my electric field points which direction? This way. Good. Right to left. So this is my electric field. Right? Now what I know is that this charged particle is starting off here with a velocity of V0, ends up over here with a final velocity of V, which is less than V0, which means is it speeding up or slowing down? Slowing down. So that means the direction of the acceleration has to be which way? Good, in this direction. So we know this thing has to feel an acceleration this way, which means what has to be the direction of the force on this guy? Same direction. This guy has to be feeling a force this way, which means the force is in the same exact direction as the electric field, which means is it a positive charge or a negative charge? The positive charge. So since this guy's a positive charge, is it a proton or an electron? It's a proton. Good. So part A, we know that this guy is a proton. Since the force is in the same direction as the electric field. The other way we can say this is we also know it's positive because it is slowing down when it goes from a low potential to a high potential, where it has to be speeding up going from a high potential to a low potential. So it's doing the opposite once it's, so it's slowing down. Either explanation is fine. Good. So now that we know that, next part is we want to know what is the speed by the time this thing reaches the second plate. So good. So in this case, we're going to use our newfound friend, conservation of energy. So conservation of energy says that the work done by the non-conservative force is equal to the change in kinetic energy plus our change in potential energy. Now, first things first, do we have any non-conservative forces in this problem? No, there's no air resistance, no friction, no anything like that. So the left-hand side is simply going to be 0, as Maddox told us earlier. Right? Now, what's pretty much always going to be true with these problems is this will always be a true state. Right? So it's always pretty much going to be 0 on this left side. Right-hand side then is going to be equal to what? The final kinetic energy, which is 1/2 the mass of the proton times the final velocity squared minus 1/2 the mass of the proton times the initial velocity squared, plus, using this guy, the charge, which in this case is the fundamental charge, since it's the proton, times our change in voltage. So this is using that our change of potential energy is equal to the charge times the change of potential. In this case, we know the charge is the fundamental charge since it's a proton. Is okay?
You said the initial result is growth, right? So that's why we don't have like
In this here, well, this is just change. Simply change. So in this case, I know the difference between these two is just 20 volts. So whether I use it as -50 minus a -70, so that's going to give me a -50 plus 70, which is 20, or I use it as 20 minus 0. Oops, threw my chalk, broke it. It doesn't matter. That is just that guy. I mean, I could write that as the final potential minus the initial potential, but in this case, I already know what the change is. It's simply the difference in these two numbers. So I'm just going to leave it like that. So great. Only thing I want to know now is this. So I'm going to add these two to the other side. So I'm going to get a 1/2 m proton times the final velocity squared is then equal to 1/2 m proton times the initial velocity squared minus the fundamental charge times the change in electrostatic potential. Finally, all I'm going to do is multiply Zold by 2, divide by the mass, and take a square root. So I find the final velocity then is going to be the square root of 2 divided by the mass of the proton times all that other stuff in parentheses. Plug in my numbers. What I find in this case then is that the final velocity, putting it back into kilometers per second, works out to be, I'll write it down here, 65.29 kilometers per second. Okay, nice, easy problem. Just to remind you that fundamental charge is 1.602 times 10 to the minus 19, and the mass of the proton is 1.67 times 10 to the minus 27 kilograms. Don't worry, in about a week or two, all of these numbers will be embedded into your brain for a while. We're going to use them a lot. Okay, let's do one more. So this one says that we have an electron in a cathode ray tube is accelerated from rest through a potential difference of delta V or VBA, whichever you want to write it, is 5,000 volts. So it wants to know what is the change in electric potential energy of the electron, and then what is the speed that it has when it comes out through the region of potential energy. Cool. So let's write all this down. So we know that our charge in this case is negative of the fundamental charge since we have an electron. We know our change in potential, which is equal to VBA in this case, is equal to 5,000 volts. That's all the information I need for part A. So part A then is asking, well, what is the change in potential energy? Well, we now know the change of potential energy is related to the change of potential by what? Q, the charge, right? So this is going to be then equal to simply Q times my change of potential, which is going to be equal then to negative of the fundamental charge times my change in potential. Plug in my numbers for that. What I find in this case then is that my change of potential energy is going to be negative 8 times 10 to the minus 16 joules. Oh, now it doesn't have to work. You can do it. Kind of. Not very happy. This is what you were supposed to say earlier. So, where'd my magnet go? There it is. So yeah. So again, if I move my magnet around, I can cause the beam to deflect. And that shows that it's actually a charged particle, and we'll talk about why I know that later. But yeah. So again, that's all that's happening here. So again, this is basically two parallel plate capacitors. So I got one plate here, then creating a constant electric field in between, causing this guy to accelerate from one side to the other. You had to make me a liar in the beginning. Okay, so, it was okay. Just needed time. It was on a break. So great. So now let's talk about part B. So part B is saying, okay, here is my region of delta V, which again we know is equal to 5,000 volts. Okay. So basically what's happening is my electron, so my Q is equal to negative E, starts off in this region, and we're going to assume it starts off with 0 velocity. So my initial velocity is equal to 0. Now, what it's doing is it's going to be accelerated. It's going to accelerate all the way through this region until eventually it comes out through the side here, where it's going to be moving at some final velocity. So all I want to know is, what is that final velocity it has by the time it comes out? Now, in this case, the only thing I know is my change of potential. So let's use conservation of energy again. So we're going to say that for part B, we have 0 is equal to our change in kinetic energy plus then our change in potential energy. In this case, our final potential energy is going to be 1/2 the mass of the electron times the final velocity squared minus 0, since the initial velocity is 0, minus my charge times my change in potential. Or I can leave it as plus change of potential energy, just use this number as a negative, but either way is fine. From here, only thing I want to know is, what is the final velocity? So I'm going to add this term over here, multiply by 2, divide by the mass, and then take the square root. So finally I get, this is the square root of twice the charge times my change of potential divided by the mass of the electron. Like my numbers, what I get in this case then is, this works out to be about 4.2 times 10 to the 7th meters per second. Now I'm going to throw up a little asterisk here. So one thing that's going to be true is if you ever get that this V here is greater than, so if you find that V is greater than 3 times 10 to the 8th meters per second, automatically you know you did something wrong. And this is not physically possible. Reason for that is that's the speed of light. We'll talk about that by the time we get to the end of the class. Speed of light is about 3 times 10 to the 8th meters per second. Nothing can travel at the speed of light. So if you travel and you find something moving at or faster than the speed of light that is not a massless particle, then you know you messed up somewhere. Let's go back and check your numbers, okay? It's okay? Not too bad. Not too bad. So good. So now let's start talking about the relationship then between the electric field and then the potential. So now we have this thing, the electrostatic potential, this V. We also have the electric field. Turns out that these guys are related to each other. What we want to know then is, how are these guys actually related to each other? So to answer that, let's go back to saying that what? Let's go back to our definition of work. So we know work is going to be equal to what? So based on what we just found, we found that this was the charge times the electric field and I'm going to say only the electric field in the x direction times then the distance at which this thing traveled. So meaning that whatever cosine portion is going to be part of the e sub x. Okay, so this is only happening in the x direction. And we also know that now this is equal to minus my change in potential energy, which is then going to be equal then to minus my charge times my change in electric potential. Now, if I look at these two portions, what this tells me then is that what? The charge is the same, so let's get rid of the charge. So finally, this tells me then that the x component of the electric field times the distance is equal to negative my change in potential. Or finally, the x component of the electric field then is going to be equal to negative the change in potential divided by the distance d. Right? So what this tells me then is a couple different things. So first of all, this tells me that what the electric field now has another unit to it. So before we saw it had units of newtons per coulomb. This thing has units of volts per meter. So this is another unit, where a volt per meter is exactly the same thing as a newton per coulomb. So this is just an alternative way of writing that. What this also tells me is that what? The electric field then points in the opposite of the direction of the change. So this negative sign means that the electric field then points from high potential to low potential. Which, going back to what we had drawn over here, makes sense. Because again, when we said this was the positive plate, this was the negative plate, we said this was the high potential, this was the low potential. Our electric field, we know, points from the positive charge to the negative charge. So our electric field pointed this way. So this says that, again, our electric field points from high potential to low potential, which is exactly what this thing is saying. Right? The other thing that this thing says is that the only way an electric field exists is there has to be a change in potential. Right? So meaning if I have a going from point A to point B, if it's at exactly the same potential, there is no electric field. So to have an electric field, there has to exist a change in potential. So a change in potential as a function of position gives rise to an electric field. This is very similar to, going back to this, the fact that this thing moves from this position and this position, so it goes from a high potential to a low potential, is because a force exists. That force is what we call the gravitational force. But if I move from this position to this position, there is no change of potential, therefore there was no force. So what this really means is that a force is a manifestation of a change in potential. If there's no change of potential, there is no force. So what is more fundamental is potential, not electric field, or potential energy, not force. So potential energy is more fundamental than force, which means electrostatic potential is more fundamental than the electric field. But ultimately, this is the relationship between the two. So what this says then is that this thing has an electric field if my potential changes moving in the x direction over some distance. The size of the electric field then is determined by how quickly this thing is changing. This is just the slope of the line. The bigger the slope, the greater the electric field. The smaller the slope, the smaller the electric field. But the direction of the electric field itself points in the opposite of the direction of the slope. Okay with all this? No, it's a lot of things to be thrown at you there for a second. It's okay. Good. Now, the potential that we're going to be the most interested in, though, is the potential of a point charge. So let's look at the electric potential, electrostatic potential, I should say, electrostatic potential of a point charge. So good. So now we've looked at the force between 2 point charges. We've looked at the electric field from a point charge. So now let's look at the potential of a point charge. So the potential of a point charge is actually equal to K times Q, all divided by R. So this is the potential of a point charge, or the electrostatic potential of a point charge. So what does this mean? So this means that if this is my point charge sitting here, this guy has a charge Q to it. This is my point R, which is some distance away from the point charge. Then this is the amount of potential that this thing has at this point. Now, the answer to this is it's actually a little bit more subtle than this, because what this is actually a potential difference, which means this is actually a voltage. So this is not just a value of the potential, this is actually a potential difference between 2 points. Those 2 points are this point, which is some distance r away from this point charge, and all the way hell out at spatial infinity, where the potential is actually equal to 0. So this here, there's an assumption, where this assumption is that the potential is equal to 0 at r is equal to infinity. This is our reference point. So for a point charge like this is the reference point. The reference point where the potential is 0 is all the way out at infinity. So by saying that my potential at some distance r away is kq over r, what that really means is that I'm taking my voltmeter, here's my voltmeter, where I'm putting one wire at this point, and I'm putting the other wire way out here at spatial infinity. And then the potential difference between this point here and this point here is that amount. That's what this thing actually means. So it physically means that the potential difference between this point, some distance r away, and where it's 0 at spatial infinity is that number. That's what this thing actually means. Now, notice here, there is no absolute value around Q, which means that this thing is positive or negative depending on the value of Q. If Q is positive, the potential difference is positive. If Q is negative, the potential difference is negative. So in this case, there is no absolute value. Now, this thing, just like potential energy, is a scalar value, which means it doesn't depend on direction, which means the potential at this point or any point along this circle is exactly the same. It doesn't depend on direction, which means if I'm here, it doesn't point in a direction. If I'm here, it doesn't point in a direction. It is just that value at any point, which is the same distance it is away. Right? But again, this is the potential at this point relative to spatial infinity, where the potential is equal to 0 at this point. This is for 1 point charge. What happens if I have more than 1 point charge? Well, the total potential at a point is then simply going to be equal to the sum of all the potentials from all of the other points, all relative to infinity. So again, our superposition principle. So the superposition principle says that if we have multiple particles, then the total potential at a given point is simply equal to the sum over all possible potentials. So this was Q1, this was say Q2, this was Q3, this was my point of interest. Let's call that point P. And this is some distance R1, this is some distance R2, this is some distance R3. Then in this case, we'd say that the potential relative to spatial infinity at point P is then just going to be the potential from particle 1 plus the potential from particle 2 plus the potential from particle 3. Or again, in summation notation, this is going to be the sum over I of the potentials at point P. That's the potential from the first charged particle at point 1 plus the potential of the second charged particle at point P plus the potential from charge 3 at point P simply added together. Now again, this is a scalar summation, unlike electric fields, which is a vectorial summation. Which means here there are no direction properties to it. All I'm simply doing is adding numbers together, unlike the other one where I have to add components, right? I have to look at directions, angles, geometry, all that beautiful stuff. In this case, I don't have to worry about any of that. So cool. Let's do an example. So this says, what is the potential at point A, or point P, if you want to call it, in this particular figure here? So let's draw our figure. So good. So what I have is here's my y-axis. Here's my x-axis. So I have my two particles along the x-axis. So they're both, what, 26 centimeters away from each other. One is a positive charge, one's a negative charge with the same magnitude of charge. Good. So this one is here. So Q1, we're told, is minus 50 microcoulombs, where again, this is 26 centimeters. 26 centimeters on the other side of the origin. I have Q2, where Q2 is a positive 50 microcoulombs, which again is 26 centimeters. Point P then, or A in the problem, but I'm going to go with point P for now, is some distance, which is what, 30 centimeters above Q2, which means that it is 60 centimeters away from Q1. What I want to know in this case then is, what is the total potential at point P? Okay. So let's go ahead and work through this. So we know that this is now going to be equal to, by our superposition principle, the potential from charge 1 plus then the potential from charge 2. Now, using what we just defined the potential to be, so this is going to be equal to K, okay, times charge Q1 divided by the distance, let's call that R1, plus KQ2, all divided by the distance R2. Where according to this is R1, this is R2. So R1 is going to be 30 centimeters or 0.3 meters. R2 is going to be 60 centimeters or 0.6 meters, because those are the distances they are away from those positions. Okay. From here, all I do is plug in my numbers. So they both have K, so I'm going to pull the K out front. So I get a 9 times 10 to the 9th times. So this is then going to be a minus 50 microcoulombs divided then by 0.3 meters plus positive 50 microcoulombs, all divided by 0.6 meters. Now, because I'm lazy and I don't feel like multiplying out the 50 microcoulombs multiple times, I'm just going to factor out the 50 microcoulombs because, you know, no sense multiplying by multiple times. So ultimately, I'm going to get a, what, 9 times 10 to the 9th times a 50 microcoulombs. So that's 10 to the minus 6 coulombs times then 1 over 0.6 meters minus a 1 over 0.3 meters. Plug in my numbers. What I get in this case then is this works out to be I have the right values here. So this should be about 7.5 times 10 to the 5th volts. Oh, sorry, I have the positive and negative wrong. There we go. That makes more sense. Okay. Sorry, I wrote Q2 as negative, but Q2 was positive, not negative. Sorry, I switched the order of these two. Yeah. Gotcha. Is okay? Let's do another example. So with the same picture, what this says then is how much work is required to bring Q2 into its final position near Q1 in the figure below. Okay. So what this question is basically asking is how much work did it require to assemble this charge configuration? This is what the question is basically asking. So it wants to know if initially this was empty space, how much work was done to assemble this charge configuration? This is what we want to know. So let's get rid of all this. Ultimately, this wants to know what is the total amount of work which was done to assemble the charge configuration. So let's talk about this. So let's say initially I have nothing here. So this is just an empty board. Now what I'm going to do is I'm going to go all the way out to infinity. So here's infinity. I'm going to grab Q1, bring Q1 in. and then I'm gonna drop it here, okay? So it means I had to do some work to do that. So the first thing we want to do then is find out how much work did it take to bring in Q1. Then, now that Q1 is sitting here, now I'm going to go all the way out to spatial infinity, grab Q2, and now bring Q2 in and drop it here. So now we want to know how much work did it then bring in the second charge after the first charge existed. Then the total work is simply then going to be equal to the sum of those two works. Okay, this is going to be the total amount of work. Now, let's think about this. So let's say initially, nothing is here. So if nothing is here initially, how much potential is here initially? 0. There's no charge, there's no potential, right? So initially there's 0 potential. I come all the way out here. And how much is the value of the potential all the way out here? 0, because it's spatial infinity. So I'm going to grab this charge, which is at 0 potential, and I'm going to bring it all the way into here where there's now 0 potential, and I'm going to drop it. So what's my change in potential going from 0 to 0? 0. So the amount of work I did initially is absolutely 0. All right? And the reason I know that is because remember our work, which is then equal to the charge times our, actually negative of our charge times our change of potential, because work, remember, is equal to negative the change of potential energy. Well, again, I'm going from 0 potential to 0 potential, so my change of potential is simply 0. So in this case, this is going to be equal to negative Q1 times 0, which is then equal to 0 joules. So I had to do 0 work to bring in the first charge. Okay? Not too bad, right? I did it for free. Didn't have to do any work. Now let's talk about Q2. So now Q2 is now, grab this one, initially way all the way out here at spatial infinity. So how much potential is it in out here? 0, right? By definition, it's at spatial infinity. There is no potential. So I'm going to bring it from 0 potential, but now I'm going to bring it in and I'm going to drop it here. But is there now a potential here? Yes. From what? Q1. So what I'm going to do is I'm going to drop this into the potential that Q1 is creating at this particular point. Which means in this case, my change of potential is no longer 0, but it's going to be the final potential, which is the potential from Q1 at this point, minus my initial potential, which is 0 in this case. So let's write that down. So this is then going to be equal then to what? Negative Q2, because this is the charge that I'm moving, times then my change of potential. Well, this is going to be negative Q2 times my change of potential, which is going to be what? The potential from the first charge, minus then the original potential it was in, which is simply equal to 0 in this case. Cool. Now, V1, though, we now know, based off of it's a point charge, this is then going to be equal to negative Q2 times K times Q1, all divided by the distance between the two, which is going to be this distance, 26 plus 26, or in this case, 0.52 meters. It's okay. From here, I plug in my numbers. I have minus 50 microcoulombs times K, which is 9 times 10 to the 9th. Q1 is a negative, another negative. So I get a negative and negative, which is going to make this guy positive. And then divide by that. So plug in all my numbers. What I find in this case then is this works out to be like 43.3. Okay. So this means my total work then is simply going to be equal to 0 plus 43.3 joules, or simply 43.3 joules. So in this case, I had to do a total amount of work. Well, actually, the electric field did a total amount of work of 43.3 joules. Now, this goes back to one of the things we were talking about yesterday. to interpret who did the work in this case, we have to look at the sign of the work. In this case, this is specifically the work done by the electric field. Since the work done in this case is positive, does that mean the electric field itself did it or something else did it like me? So we mentioned this yesterday. So whenever the work is positive, does that mean it did it or something else did it? Actually, that did it, right? So whenever the work is positive, it means whatever this object is had to do the work. If the work was negative, that means an external thing had to do it. Now, in this case, does that make sense? So we're saying in this case that since the work done by the electric field is positive, that means the electric field itself did the work, where it's bringing a positive charge close to a negative charge. Does that make sense? Caleb just said yes, right? Because what do we know? We know that a positive charge is attracted to a negative charge, so it wants to be close to it. Now, what would be different if this was a positive and positive charge? We get a negative, right? Because now we wouldn't have the negative here to cancel this negative, which would make this guy negative, which means in this case, we would get a total work, which would be negative, which would be consistent with the fact that we have two positive charges, because what do two positive charges want to do? They want to get the hell away from each other, right? So I have to physically go in and force them to be close to each other because they don't want to be near each other at all. Right? So in this case, it makes sense that the work is equal to a positive value because the electric field itself did the work because I have a positive charge with a negative charge. They want to be near each other. But if I had two positive charges, they don't want to be near each other. So in that case, again, it would be a negative work. So the sign of the work is very indicative on who actually did the work. So in this case, since we're looking at the perspective of the electric field, the positive means that the electric field itself did the work. Okay, like I said, this will be important for a second exam. There will be part of a question that asks you this: who did the work? Make sure we understand it. It's okay. So let's do another example. Example is that number 4 or 5. Okay, look at this one. So this says we have a small metal sphere carrying a charge of Q1 equal to negative 2.8 microcoulombs is held stationary by some insulating support. A second small metal sphere, which has a charge of negative 7.8 microcoulombs and a mass of 1.6 grams, is projected towards Q1. Then says when the two spheres are 0.8 meters apart from each other, Q2 is moving towards Q1 with a speed of 22 meters per second. So let's draw our picture of all this to work onto a picture. So here is, say, my insulating post connected to the small metal sphere, which has a charge of Q1, which is equal to negative 2.8 microcoulombs. Over here, I'm going to have the other small sphere. So here's my other small sphere moving to the right with a velocity of, what was it, 22 meters per second? With a charge Q2, which was negative 7.8 microcoulombs, and they're a distance of 0.8 meters apart. Okay. Then says neglecting the effects of gravity, so meaning we're not going to worry about this thing falling downward. What is the speed of Q2 when the spheres are now simply 0.4 meters apart? And then finally, how close does Q2 get to Q1? So let's look at that. So now what it wants to know is when it has transversed half of this distance, so now it is sitting here, what is the new velocity v? So let's call this guy v initial. And let's just call this guy the velocity v. So for part A, we want to know then is how fast is this guy moving at this point? And finally, we want to know what is the absolute closest this guy gets to the other guy. So meaning that finally at some point, Q2 is going to be here, and we want to know what is this distance here. So what is the let's call this R min. So what is the minimum distance this guy's going to get away from him? So for part B, we want to know what is R min. Okay. Now, first thing I'll point out in this problem is there is no way we could use forces to do this problem. And no way we could use kinematics to do this problem because what do we know? We know that in this case, this is 2 point charges. We know the distance between the 2 point charges goes as 1 over r squared, which means the acceleration goes as 1 over r squared, which means the acceleration is position dependent, which means it's time dependent, which means it is not constant, which means can we use kinematics? No, right? If we know how to solve integrals and differential equations, all kinds of fun stuff like that, we can do it. But that's not this class, so we have to use something else. The only way we can do this problem is conservation of energy. So in this case, we have to use conservation of energy. So for part A and for part B, we're gonna use conservation of energy. So we have 0 then is equal to our change in kinetic energy plus our change in potential energy. And it's 0 again because we have no non-conservative forces in this case. Change in kinetic energy is going to be equal to what? So we're going to have a 1/2, gave us mass, right? Yeah, so we have the mass times then the final velocity squared minus 1/2 the mass times the initial velocity squared, plus our charge. So this is actually going to be a negative since we have a negative charge. So I'm going to write as plus anyways. So I'm going to write as Q2. We'll use the fact that it's negative later. Times my change in potential. Now, what is that? So let's call this distance here our initial. And then let's call this distance here, which is our 0.4 meters, simply r. Okay. Now, as far as Q2 is concerned, what is creating the potential at R0 and what is creating the potential at R? Those guys moving in a potential. Who's creating that potential? Well, that's what's creating the kinetic energy. Well, Q1, right? So Q1 is creating the potential both here and here. So this is going to be equal to the final potential by Q1 minus then the initial potential from Q1. Okay. So in this case, this guy is moving in the potential of another point charge. So this is the guy that's creating the potential that this guy is moving in. Okay. Now, let's put some more stuff in. So this is then going to be equal to 1/2 the mass times the final velocity squared minus 1/2 the mass times the initial velocity squared plus the charge times. So it's going to be K Q1 divided by the final distance of R minus then K Q1 divided by the initial distance of R0. It's okay. I'm going to do one more step before I start doing some algebra here. So again, K here is the same as this case. I can factor it out. Q1 here is the same as Q1 here, so I can also factor that out. This one I have to multiply the same number multiple times. Again, I'm lazy. So there's 1/2 m v squared minus 1/2 m v initial squared plus K Q1 Q2 all times 1 over R minus 1 over R0. Now, in this case, Q1 is negative and Q2 is also negative, which means that those two negatives are going to cancel each other, which makes this guy positive overall. So from here, what I want is this V. So I'm going to add these two terms over here, multiply by 2, divide by m, and then take a square root. So let's write all that down over here. So finally, I get a V is equal to the square root of 2 divided by the mass times then 1/2 m times the initial velocity squared minus K times Q1 Q2 all times 1 over R minus 1 over R initial. That's what I mathematically get after doing that. Numerically, I would just plug in all my beautiful numbers here, and what I find is that the final velocity is 12.5 meters per second. So this is the final velocity after it has undergone half of the distance to the second guy. Is okay? Part B, we're basically going to do almost exactly the same thing, except now the only difference is we want to find out what is the minimum distance that this guy approaches to him. which means what has to be true about the velocity by the time it gets to this point? Has to be 0, has to momentarily stop. So the only thing that's going to be different is that this final velocity is going to be 0. We're not going to know what this final position is. This is what we're going to be solving for. It's basically the only difference. Right? So let's sketch all that down. So for part B, so the only thing that's going to be different is our final velocity here is going to be 0. So this term here is going to be 0. And this is now going to be, again, our final. But our final in this case is simply going to be R min. Basically going to be the only difference. Now again, I'm going to have an R min here. And again, this is simply going to be 0. That's it. That's the only big change. From here, doing the algebra can actually be kind of a pain in the butt. So just have to do a lot of inversions and all kinds of different stuff. So if you want, I can do all that for you, or if I can just kind of skip it right down with the answer. So which one do you prefer? Okay, I'll give you the answer. So we find that R min then is going to be equal to about 0.32 meters. So the closest this guy gets is actually not too much further than the halfway distance between the two. So it starts off at 0.8 meters, gets to 0.4 meters, and then it's only going to make it a little bit further before it actually momentarily stops. And the reason for that, again, is because remember the force is 1 over r squared, right? Which again means the closer this guy gets, the force drastically increases as it gets much closer. Jabin, what's up? You could solve for r. The only difference is if I went from this r, I would have to take this velocity that I just erased into account here. So this wouldn't be 0. It would be the 12 points, whatever. Yeah. So that'd be the only difference. If I went from the 0.4 meters, so you're right. So if I could do 0.4 meters here, but then this would be a non-zero term here. That'd be the only difference. But yeah, it doesn't matter if I go from the 0.8 or from the 0.4, I still would get the same answer at the end of the day. That's right. I just like doing it going all the way back because now I'm dealing with given numbers and not something I calculated at 0.4 meters. Okay? Because I may have calculated this velocity wrong. And now I have a wrong number automatically in here, which will automatically make my next one wrong. But not a huge deal. But what's up, Jackson? Yep. Oh, so if you did part B absolutely correct from a wrong part A, you would get all the points for perfect. Yes. Yeah. Yeah. Yes. Absolutely. Absolutely. Maddox.
So when Q2 gets close to Q4,
Yep.
it stops when it gets close to as close as it can get. What happens to Q2? Does it just like go back?
It's going to go back. Exactly. It's going to basically slingshot back out.
Would it go at a faster velocity?
Well, it should do exactly the same thing going in the opposite direction. So by the time it gets to this point, it'll have 12 points, whatever the velocity was in this direction. By the time it gets here, it's going to have 22 meters per second in this direction. The reason for that is that it's symmetric going in both directions. So the force at this point, regardless of going this way or this way, is still pointing in this direction with the same acceleration. So the only way it would have more velocity here is if it momentarily stops and then I kicked it to give it more kinetic energy to move backwards faster. But otherwise, no, it's just going to momentarily stop, turn around, and then do exactly the same thing, just in the opposite direction. Because there's nothing injecting more energy into the system. So. I don't think so. Sorry, I'm talking to myself at the moment. So great. So we'll end today. Of course now. So tomorrow we'll be able to quickly finish this up. So we've got to talk about equipotential surfaces, and we'll start talking about capacitors. So we'll spend some time about that, and then we'll be done with this chapter. Life is great. Yeah, I'll do all that tomorrow and everything. Yeah. I also graded your exams, but they're sitting on my kitchen table. Apparently, I forgot to put them in my bag, so I'll bring them with me tomorrow. I'll post the points on Blackboard during lab, so that way you can see your points beforehand, and then I'll pass them out tomorrow. So one thing to be important about the points I put on Blackboard, that'll only be your raw score. So no extra credit in it at all. Because remember, as I said in the beginning, extra credit, we're going to scroll to the side and just dump it on top of everything at the end of the day. So yeah, so don't worry about your extra credit. That'll also show up on Blackboard. Life will be great. Okay. No, I was pretty happy with what you guys did. I was pretty happy. What was that? Can you start again?
Semester or even Friday? For the extra credit being added.
Oh, at the end of the semester. Okay.
So I'll just live in an anxious state.
Well, I mean, you'll know what it is. I mean, so basically, yeah, because on whatever you get on the exam itself, I'll just write on the exam, this is how many extra credit points you got. And then when I grade the ones that are on Blackboard, Blackboard will automatically be populated with those extra credit points. And then, yeah, so then basically all I have to do is take whatever your averages are, blah, 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 and then just dump all those points on top at the end. So it'll help definitely boost up your scores. Yeah. Or you can always ask me at some random points and stuff.
Hey, Mr. Greenwood, before you erase all that,
Yes.
could I get a close-up of that final equation on the right?
Or sure. Okay.
Okay, I got it.
Oh, okay.
Thank you. Oh, good.
Okay.